Okay, I'll show you the program, which is synchronous parameter. This is the program. Okay, I will upload it to you. Well, success generator parameters, the transient and subtransient, how we calculate them. We assume that IA here, IA is equal to three components. This is the envelope of the current. I steady state. And then A1 exponential minus H1 times T, which is the transient component, and then A2, which is this one, the subtransient component. Here, H1 means that it's 1 over the time constant transient, and H2 is 1 over the subtransient time constant. So, if we start IA naught equal IA at time equal 0, and then K naught is IA naught as I described to you in the previous video, and K naught is A1 plus A2, so we have to calculate what is I1, and we assume Y is IA minus I steady states, which is equal to this. Okay, so we substitute A2 by K naught minus A1, since we know the summation of A1 plus A2 equal K naught. Then we clear the screen, the first one. E maximum assumed to 1, but you have to put it in the project, see how much it is, and you have to put it, okay? E maximum could be 1, could be different. Time is from 0 to 0.05 and is 2. Check in your project what time steps you can make, or you can take T. It's not necessarily to be equally displaced. You can take 0, 0.05 and 1.5, 0.15, and it doesn't matter. And IA, we just as we assume that IA is as in our example, okay, is 2.5. When okay, here we can change. We started with subtransient and then the transient. Doesn't matter whether you bring this to this side or this. It doesn't matter. Okay. And I steady state is 1 in our example. Y is IA minus I steady state. So IA we have determined it this way, but in reality it should be tabled from the results of the experiment. IA naught is 5 in our example. So K naught is 2.5 plus 1.5. So K naught is A1 or A2 plus A1. Okay, so we know it is 2.5 plus 1.5, so it will be 4. For the project, you must determine IA. Okay, I steady state, IA naught, that's at time 0. Experimentally, you must determine them experimentally. Okay. Assume reasonable values of A1, H1, and H2 for starting. Okay, A1 initial, H1 initial, H2 initial. I just put 330. Okay, and A1 naught is K naught over 2. That's a good start. K naught over 2 is a good assumption. Okay, for the start. Then we put A1, H1, H2 equal to the values we have assumed. That's for the starting. Then we start the iterations. Start iterations using Newton-Raphson method. And we want to stop the iterations when the tolerance is 10 to the minus 6. So we print the iteration and the maximum of the absolute value of f. I put here maximum iterations 1000. Okay. F is equal A1, okay, that's the function f, okay. Then the index is y minus f times half squared, half y minus f squared. Okay, that's the index, or j. Then we take the derivative of that index with respect to a1, with respect to a2 or h1, and with respect to h2. So these are the first. F1 represents the derivative of the index with respect to a1. F2 the derivative of the index with respect to h1. F3 the derivative of the index with respect to h2. Okay, you'll get these ones. Okay, then we calculate the Jacobian. Okay, 1 1, that's df1 with respect to a1. 1 2 is f1 with respect to h1. 1 3 is f1, our derivative of f1 with respect to h2. Similarly, Jac 2 is the derivative of f2 with respect to a1. Jac T2 is the derivative of f2 with respect to h1, and Jac 2 3 is the derivative of the second function f2 with respect to h2. Jac 3 is the derivative of function 3 with respect to the parameters. So 3 1 is the derivative of f3 with respect to a1. 3 2 is the derivative of f3 with respect to h1, and 3 3 is the derivative of f3 with respect to h2. Then we formulate the Jacobian. 1 1 1 2. That's the first row. Okay, and this is the second row, and this is the third row. Okay, now we know Jac. Then we invert Jac times this one. Okay, times f. Okay, that's f, f1, f2, f3. Then we update a1, h1, h2. Okay, is the previous a1, previous h1, previous h2, minus, okay, minus Jac inverse, or inverse of Jac, times f1, which is d. We have calculated 1. Okay, I put here 1. You can you can use if you find problems in divergence, you can reduce this one, make it 0.1, 0.2, and so on. Okay, it will slow down the convergence, but it can make it succeed. Okay, then we calculate the maximum f, which is absolute of f1, f2, the maximum. If that maximum is less than the tolerance, and we'll print it also. If the maximum is less than tolerance, we break the loop. Okay, so we can achieve convergence before the 1000 iteration. Then we end the iterations. This will end the program. Tau transient is 1 over h1 or 1 over h2. We take the maximum. The maximum out of those is the transient, and the minimum is the subtransient. Okay, now we want a1 to belong to the transient and a2 this transient. So if 1 over h1 is greater than 1 over h2, which means that this time constant is greater than the time constant, it means a1 we have calculated is correct, and a2 is k0 minus a1. Otherwise, we replace a2 is equal to a1, and then we calculate a1. Because we wanted a1 to represent the value of the transient component, while a2 represents the value of the subtransient component. If we go to the original function, which is this one, okay, this is the function a1 here, a1, and here a2. Here is h1, and here is h2. It may happen that the a goes to a2 in this side, or this a2, okay, this one or this one. We want it doesn't matter what is the value of this one. The most important is this one. Now, if this one is larger than this one, then this is a1. okay? But if it happens that this is smaller than this one, it means this is A2. That's exactly what we are doing in this step here, okay? Then we calculate XD, E maximum divided by I steady state, then transient, we add to I steady state A1, sub-transient, we add it A1 plus A2, or K naught. You can insert here K naught, okay? Now, this is just printing the parameters, okay? We can start this by just, let me go and set the path here, set path, because I put the path somewhere, add a folder, and this folder is somewhere here, I put this here, but you can put it just directly, and you know how to do that. Select the, okay, and then we go, I don't want to save it. So, okay, I will run this program. Okay, now, if you look at it, iteration 1, it succeeds after 9 iterations. This is the maximum, so it becomes less than 2. This is less than 10 to the minus 6. Then it will print out the machine parameters. A1, A2, 1.5, 2.5. H1 is 2.5. H2, okay. 1 over H1 will give us the tau, okay. The tau transient, which is 0.4. 1 over H2 will give us the tau subtransient, which is 0.02, okay? Now, what else you must make sure that your solution is correct, you need to plot. What I'm plotting against T, what was Y, give it a mark X, and what was F, okay? If we go back to F, if we are calculating, this is IA and this is F, okay? We are calculating F here, this is F, okay? We want this to be exactly or very near Y, okay? The variable Y, okay? This is Y minus. In fact, we are trying to minimize Y minus F squared times half. So when we take the derivative, because try to check the derivatives yourself, okay? So we want to make sure that Y and F are almost the same. So we can plot this one, and let's see the plot, how it looks, okay? We plot it, and now it will come. Okay, that's the plot, okay? This is the plot. You see, these are the points. This, for example, this point here, this point here, this point, this point, this point. These points are the experimental points, okay? While the solid line is the fitting function. Now you see, it's exactly similar to that, okay? Now you can. I forgot to put a line. I think line width. I'm not missing line width. I think I forgot that, and put it, for example, for. Remember that. Yes. Okay. You see that it is. It is obvious that the function and the experimental points almost the same, okay? You understand that now. Let's go back to the function here. As I told you, sometimes you may have a problem. For example, it's K naught over 2. Let's say we know that K naught is 4. So let's put a 3 and see what happens. Okay, sometimes you and run it and see. There's a problem here. You see, it's converged, but it did not converge. You see, it's there's a problem. You see, we have a warning and these things. And if you plot this, you see, they are not the same. So you are you are sure that your solution is not correct. Okay. So to avoid that, let me try to slow the convergence a little bit. Here, instead of 1, let me put 0.1 and see whether it will succeed or not. Just try it. Okay. Now it did not succeed even with that 1. You see, it took that so many iterations, but from the figures I looked to here, is not successful. And to make sure, just you plot that. Okay, you see, it's not successful. Let's try. If you try this, well, because we tried. Let me try 0.01 here. It may succeed, may not. Just you try. You need to keep trying. Okay. Let's see. It almost succeeded. You see, it succeeded in this case. If we plot that, okay, you see, it's successful. You know. So if you start, this means that, but it took the whole. It did not converge completely. So we need more iteration for that. Okay, we can increase it and see. How about 4 and see? It's not very successful. Okay, as you see from this here. So 0.04 is too much. Let's plot it and see. Though it is there, you see, but it means still needs more maybe iterations. Okay, A1 is supposed to be 1.5, supposed to be 2.5, near there. The transients and the transients, there's little. Okay, but at least it goes to the point. Let's make 2 here. Okay, and do it again. Now it's better, you see, and it's convert. You see, less than 1,000. The iterations less than 1,000, but more than that. And if you plot it here, plot this. Now it's successful, right? Okay. Now you learn that in Newton rhapsodes, sometimes you need to slow the divergence a little bit by controlling this. Okay, and this one depends on the starting values here. Okay, if we start at say 1.0, for example, and see what happens. Okay, let's synchronize this. Again, it is not successful as I see from here. Okay, from here, yeah, this is not right, the right function, and to know that you should plot this one. So you see, this is not successful. Okay, though it shows that some convergence is there, but it did not converge to the right point. Okay, probably we need to lower this one again for that starting value. Maybe make it 1. Okay, the all depends on the starting values of A1, H1, and H2. If you are near there, okay, we reduce this one. It was okay. Let's make it, for example, 2. Okay, and 2 is better, I think. Better convergence you get there. Yeah, better convergence. It converges almost. You see, near 1.5. Okay, and this is near 0.4. It's not near 0.2. You can start also reducing this to 1 and see. Okay, and do it again. Okay, and here it's also succeeded, but we need more than 1000 iterations. Okay, now we'll go to 0.01, increase it to 0.02 and see what happens. Okay, it is successful. Okay, with 677 iterations. If you can plot it and see, okay, it's there. You can increase it to reduce the iteration and see. Let's make it 0.05, for example, and see what happens with that. Okay, now again, it is not very successful. Okay, 0.05 is too much for that, because mainly, you see, there's a little difference. Okay, little difference there. Okay, so it's not very successful, though it shows that it's near that solution. You can make it 0.04, for example, and see what happens. Okay, still, okay, all depends on the iteration. So 0.04 is not good. 0.03, let's see. Again, okay, again, it's not very much successful. Okay, if you go to 0.02 and see what happens. Okay, you can reduce it. Now it's much better. You see, it's very much successful with 677. All this depends on how you start your values here. But if you start K0 over 2, okay, and do it again, you see, it's successful, but it took 743. You can start increasing that, increasing this 0.02 to say 1, and see even, yes, much. It is almost the same answer. It's okay, successful, but you reduce the iterations, and you go by that. Okay, 2.5, for example, to reduce the iterations and see whether you have a problem, you don't have a problem. So even you can go to 1.0, and do it again. Okay, you see, it succeeded with less than 10 iterations. And when you plot it, okay, plot that, you have it there. Okay, this is the way how you, this is an almost exact routine to calculate the parameters. Okay, so this program, you can practice it. Most important that you know, you can play with these starting values, okay, but K0 over 2 as starting for A1 is reasonable, and it's a good start. Okay, here also it affects, for example, if we take this 20 and see what happens. Just you need to keep trying. Okay, it's not successful. Okay, it's not successful in that. It means probably you need to reduce with this starting value. You need to reduce this one from 1 to, let's say, 0.1 and see. Okay, so if you face a problem like this, what you need is to try to slow down the convergence and see what happens. Now you see successful plot. Okay, so thus you learn that usually in Newton-Raphson, okay, you improve the solution by slowing the convergence by this method. Okay, by this one here. Let me just write that to you. Okay, and I don't have just I have a paper. I'll write to you that. Okay, I don't have a pen here. Also, what I need is just, okay, you know that x k plus 1 is equal xk minus Jack inverse times f. So that's basically, if you look at this one here, this is basically the routine of the Newton-Raphson. This is the normal routine, but you can add k here. Add, let's say, h here, for example, where h is less than 1. If you add h, multiply that. That's what we are doing here. Okay? H less than 1 will improve the solution. It will slow the convergence a little bit, but it can improve. So when you face a problem, reduce that h, okay? That's basically what we do. Okay, so this is another method of calculating the parameters. The previous video you have seen, that's the normal practical one. It's easier than this one, but again, this one you can use it in the future. Okay, when you go to practice, okay, you may use also this method, which is more exact, that one. And you can use both methods actually. The method using the linear or logarithmic scale in your project, okay, and the results you obtained from that method, you can use it as a start here, okay. It will improve the solution. I want you to try that. Okay, you will get a better values than what you have obtained. Sometimes you may not get exactly a good answer from the previous method. Nevertheless, it will be a good start for this method. The results you obtain from there, you can use it in this program to fine-tune A1, H1, and H2. Okay? So I'll send this video to you. Okay, I will send also this program on a PDF. You can type it and try it. And for those who takes 205 numerical analysis with me, you can also practice it as a curve fitting for a practical problem such as synchronous generator parameters calculation. Okay. Okay, talk to you later.